Recording has started. Hi everyone, welcome to the AIML study circle where Jamie Wasawa is the uh, presenter today for ML system design, and this is YouTube video search topic. And we had already four sessions. This is the fifth session. There were two use cases, one across the modeling, and today the focus is on ML system design. And with that, I will hand over to Jaimit Wasawa. Jaimit, I'm going to go on mute, and hopefully you will be able to handle until you come to Q&A when we'll open it out to the floor at the end. Okay. So
Sure.
note everybody will only do Q&A at the end. Just
Okay.
wait patiently and go through all the material and absorb them. Thank you very much. Welcome, Jai Mitra.
So, hello everyone, and first of all, thanks Prakash sir for the introduction. Uh, hi, my name is Jamit Osa, and today we'll be doing the presentation on the uh, YouTube video search for the ML system design, and that we have been doing till now. So, everyone is aware about the YouTube video search that we search a text query and we get the related results. So that's what will be discussing today. And also we have been following a particular framework throughout these ML system designs. And we'll be following the same kind of framework for designing our system. And those are some of the steps that we use to design the system. So first step was to clarify the requirements. So clarifying the requirements is to design a search system for videos where input is a text query and output is a list of videos similar to the text query. So as I mentioned before, it's a simple YouTube search system for videos where a text query is given and related videos are given as an output. And the videos are given in forms of, depending on the similarity score, which matches the text query. So similarity score is basically ranked from 0 to 5, 0 being no relevance or no similarity, to 5th being most similar or the exact search, and so on. So we can see that we have searched for the term videos and 3 videos are showing up. And the first video is having the similarity score or relevance score of 5. The second and third video having the relevance score of 4 and 4. So this is what we are going to discuss today, how the video should be ranked according to the relevance as well. So after clarifying the requirements, which is to have a text query, and based on the text query, we will be getting the output in terms of list of results. The second step that we follow is frame the problem as an ML task. So basically what we will be doing in this step is we translate the requirements that we have into ML objectives or ML tasks. So first is defining the ML objective to give relevant videos based on the user's text query. And the second part of the framing the problem as an ML task is specifying the system's input and output. So input is a text query and output is a ranked list of videos sorted by relevance. In the diagram below, you can see that the text query is a video and our search system will give us the result of a result as a ranked list of videos based on the relevance. After knowing the what is going to be the input and what kind of output do we want, uh, we'll be choosing the right ML category that our system falls under, or how we want to use or go further with it. So this is something that we are going to discuss about further. So this is an overview of the whole system. So starting from left, we have a text query. The text query is going to be uh, uh, split into two, not exactly split, but the text query is going to be processed in two parts. First is the text search, and the other is the video search, and both of them will be having their own results. The text search with and its own result, and the video search having its own result. After producing their own results, they will be the results of the text search as well as the video search will be fused together and will be displayed to the user. So, as you remember that the text query was lo- the text query was divided with or looked at in two parts. First one was text search, and the other one was video search. So text search deals with the textual aspect of the videos, such as titles, descriptions regarding the video, and tags that are given to the video by the user who uploads it. So in the diagram, you can see that our text query is dogs playing indoor, and our text search will be looking for the similar query, similar tags and titles, and giving us the search results. So here you can see that we are getting the result of ID1 and ID6, which are the IDs that are matched with the text query in the table below. That first and sixth ID or the entry in the table is matched with the text query. In this, we will also be using the inverted index. So inverted index basically means that the word is looked in the documents, and if the word is present in those documents uh, will be given back. So that is what. So from words, a document is searched, and the document is given back. So this is what inverted index means. So we'll be using inverted index, where each of the terms in search query points to documents or web pages that contain those terms. And for this text search, we'll be using Elasticsearch. So the other one is visual search. Now, before discussing the visual search, let us discuss a few points about representation learning as well as the embeddings. So representation learning is a set of techniques that allows the system to automatically discover the representations needed for feature detection or classification from raw data. So basically, representation learning works with raw data and learns about the hidden features and patterns about the data and helps us give the output. So representation learning and can be done in two ways, supervised as well as unsupervised. In supervised, we already have the output. So the what the model gives us as an output is has to be matched with the output that we have or the ground truth. In unsupervised learning, the model has to basically learn about the patterns or discover the patterns on its own. Representation learning works by reducing higher dimensional data to low dimensional data, making it easier to discover patterns and anomalies. Anomalies is an exception, while also providing a better understanding of data's overall behavior. Now, computer uses different kind of representations. So every unstructured data can will have its own numerical representation. This numerical representation is called an embedding. So videos, text, or audio files can have their own embeddings. So ideally, an embedding captures some of the semantics of the input by placing semantically similar inputs close together in the embedding space. An embedding can be learned and reused across models. So if you imagine that embeddings for food, and if you map those embeddings into a 2D plane, then those embeddings will be mapped in close proximity to each other. So that is why the embeddings which are semantically similar will be mapped closely or will be in close proximity to each other. And the embeddings that are produced can be used across the different models. So the visual search of the text query, the the user enters a text query and model outputs a list of videos. So rank of the videos are based on similarity of the text query and videos visual content. Similarity score are calculated by computing the dot product of text and each video in the embedding space, and then rank of the video based on the similarity score. Rank the video based on the similarity score. So each of the videos that we have in the database will be stored, and later on the embeddings will be generated or created, and those embeddings will be stored separately. Now, when the text query is searched by the user, its own embedding will be created, and that text query will have a similarity with the videos that are present in the database already, and that's how both of them will be matched and will be ranked accordingly. So in the image below, you can see that the videos are the encoder. The embedding for the video is created by the video encoder for the uploaded video, and the text query that is searched by the user is transformed into a text embedding using the text encoder. So, so after discussing a bit about the ML category that our model falls in, we'll be discussing about the data preparation that we'll be using for training the data. So first is data engineering. So we are assuming that have an annotated data set. So because we have an annotated data set, there is not much data engineering to be done. But a sample of how the annotated data set might look like is something in the table you can see. So in the table, you can see that there is also a split type. So split where training have two, the validation have two, and the one is test. So the whole data set is divided into 40%, 40%, and 20% for training, validation, and test respectively. So training set is used to train the model to learn hidden features or patterns in the data in each epoch. An epoch basically means the whole cycle of the training data that is assigned to the model or given to the model. The training set should have a diversified set of inputs so that the model is trained in all scenarios and can predict any unseen sample that may appear in the future. The validation set is a set of data separate from the training set that is used to validate our model performance during training. So model evaluation is also performed simultaneously after every epoch. The main reason to split training or validation is to avoid overfitting. So overfitting basically means more familiarity to the given data set. But if a similar kind of a data set is given to the model is not able to perform. The last split type in the while training the data set is test. So test that separates the data used to test the model after completing the training. It provides an unbiased final model performance metric in terms of accuracy or precision, etc. The feature engineering. Unstructured data is converted into a numerical representation during this step. So, so in preparing the data preparing the data, we will be discussing it in three steps, which is text normalization, tokenization, and tokens to IDs. So this image can roughly tell you what each of the terms will be doing. So a person is walking in Montreal is the sentence that we have. By using the text normalization, you can see that they are transformed into lowercase and the exclamations are removed. Now further going, uh, taking them into the tokenization, the and the tokens is created the whole sentence. So each and every word in the sentence is taken as a token, is transformed into tokens, and these tokens are given their own IDs, as you can see. So text normalization, it ensures the words and sentences are consistent. Words like dog, dogs, and dogs with an exclamation mark can mean different even though they mean the same thing. Some of the text normalization techniques are lowercasing, which means making all the letters lowercase and does not change the meaning of the sentence. Punctuation removal, removing common punctuations from the text like commas, exclamations, full stop, question marks, and etc. Time white spaces, trim, trim leading, trailing, and multiple white space means removing the spaces that are after the paragraph or some of the multiple white spaces that are given, or maybe some of the uh, characters are used uh, two times in a sentence, and those will be removed. Not alphabets, but characters. Like the other one is a NFKD, which is a norm, normalized form normalized form compatibility decomposition. So it decomposes the combined graphemes into combination of simple ones. You can see with the example that what kind of what the NFKD or normalization form compatibility decomposition does. The other is strip accents. So some of the alphabets sometimes do have their some special characters or the special version of them. So those are uh, transformed into the simple one or converted into the simple one. Sixth one is lemmatization and stemming, which is grouping morphologically similar words together. So lemmatization, and the difference between lemmatization and stemming is lemmatization keeps the dictionary form of words and keeps only meaningful words. And that is also reason it is a slow real-time application compared to stemming. And stemming is going to keep only the stem of the word. That is to keep only the root or base form of the word, and it is not going to form a dictionary form of words. So in the example of lemmatization as well as stemming, you can see that lemmatization follows a dictionary form. It will keep the words that we actually have it, and stemming it will keep irrespective of if irrespective of the word whether it exists in the dictionary, it will keep the word like in form like in the example of studies, it only keeps the studi. uh, Discussing further, the other step is tokenization, which is breaking a piece of text into smaller units called tokens. So example is let's say eat an ice cream. So all of the words in the sentence will be created into its own tokens. The tokenization has two types, which is subword tokenization, which is splitting the text into subwords. Example, the word unwanted might be split into un, want, and ed. The other one is character tokenization, which is splitting the text into a set of characters. You can see it in the example for the sentence, let us learn tokenization. So the third one is token IDs, converting the tokens into numerical values. The lookup table. First of the token IDs is a lookup table. Each token which we have created in the previous step is mapped to an ID, creating a 1-1 mapping. So in the example of the lookup table, you can see what we mean. Each of the word will be having its own ID. And the other one is hashing. Hashing is a memory efficient method which uses hash functions to obtain the IDs without keeping a lookup table. So one of the difference between lookup table and hashing is that you you cannot go get the word from the ID in hashing. If you use hashing, you it is not necessary that you will get the same word from the ID. Whereas in lookup table, you can retrieve the word back with the with the help of IDs. So after preparing the text data that we have seen, we will be preparing the video data. So as you can see in the both images, they somewhere do the same thing. The image on the right, the black and white image, you can see that there is a whole video. So the whole video is decoded into frames or separated in form of frames. Now, out of all the frames that are created for the video, some of the sample frames are chosen at random, and and those sample frames are pre-processed in from resizing to other such normalization or color correcting mode. All of those are pre-processed as well. Though resizing and scaling normalization are given in different steps, they can be happening in the same step as well before saving the file. So in this case, the file which will be saved from uh, frames will be frames.nty. So after preparing the model and after preparing the data for text as well as the video, we'll be discussing about the model development. The first we'll be discussing the model development in text encoder and the video encoder. The text encoder in text encoder, the first method to generate text embedding uh, is a statistical method is a bag of words. Bag of words converts the sentence into a fixed length vectors. It models a sentence and word occurrences by creating a matrix or with rows and rows and sentences and columns by words. So basically, the words are already ordered in the database, and the words do not contain any kind of order in terms of a sentence or semantic. If we are trying to get a meaning out of it, they are simply ordered in one manner, and depending on the words occurring in the sentence, the value of the words are given. So if the words are occurring in two times, two value is given, and so on. So the limitations for a bag of words is the method does not consider order. So as I mentioned that the saving method will not consider any kind of order, and the obtained representation does not capture semantic and contextual meaning about the sentence. So what we mean by that is, uh, for, if we have a sentence called sentence, which is first eat, then play, we can also write first play, then eat. Now both of the sentence do have different meanings, but a bag of words for both of them will be same. So this is what we mean by not capturing the semantic and contextual meaning about the sentence. Because the third limitation is because the unique vector representation is equal to the number of tokens we have for sentence. The vectors are very large and sparse and mostly filled with zeros. So if we are taking many words and comparing it and marking the sentences based on the words present in the sentence, there can be many words that are not present, which are present in the bag of words, and that's why the vector that is created from that, most of them will be filled with zeros. So in the second method for statistical method is a term frequency, inverse document frequency, which works similar to the back of words but normalizes the matrix based on the frequency of words. So, so term frequency, inverse document frequency gives a less weight to more, making the representations better than the back of words. So the limitations for term frequency and inverse document frequency is a normalization is needed and does not consider the order of words. The obtained representation does not contain the semantic meaning of the sentence, and representations are sparse. Though the limitations of both of them are almost same, and they work in a nearly similar manner, but because it's using frequency of words to create the vector, it's a comparatively smaller uh, compared to bag of words. The statistical methods are fast, but so we are talking about both the bag of words as well as the term frequency and inward document frequency. The statistical methods are fast, but they do not consider the context and semantics of the sentence and have sparse representations. So in the so for the second method for using the text encoder is our ML based methods. The first were a statistical method, and now it's a ML based methods. So sentences are converted into meaningful word embeddings so that the distance between the two embeddings reflects to the similarity of the words. So embeddings are embeddings of similar words such as rich and wealth. They will be closer in the embedding space. So in the image on the right, you can see that and the words that have similar meaning, let's say for food, for kitchen, for vehicles, the actions or the social media, all of them are comparatively in close proximity to each other. So, so if we map the embeddings of similar words, they will be in close proximity to each other. So three common ML-based approaches for transforming words into embeddings are embedding or a lookup layer, a word-to-vec, and transformer-based architectures. So first in the ML-based methods is a embedding layer or lookup layer, which maps each ID to an embedding vector. Using an embedding layer helps convert sparse features into fixed size embeddings. So you can see in the diagram below that input IDs are given into the embedding layers, and with the help of lookup layers, the embeddings with fixed sizes are formed and given as a result. So moving further with the ML-based methods, uh, second one is word-to-vec. So word-to-vec is not a singular algorithm, rather it is a family of model architectures and optimizations that can be used to learn word embeddings, word embeddings from large data sets. So word2vec is a family related model used to produce a word embeddings. The model uses shallow neural network. So shallow neural network basically means having one input layer, one hidden layer, and one output layer. So in training phase, the model learns to predict a center word from surrounding words. After training, the model is capable of converting words into meaningful embeddings. There are two reasons, there are two main models based on word2vec. One is a continuous bag of words, where the inputs are context words and the output is a target word. So for one word that we give, so for many words that we give, we get one word that is similar to the all those words that are given in an input. But in skipgram, it is a other way around, where we give the input in form of one word, and we are getting the output of other similar words. So ML-based methods for in discussing the ML-based methods, the third category is transformer-based architectures. Transformer-based architectures considers the context of words in the sentence when converting them into embeddings. As opposed to the word-to-vec, they produce different embeddings for the same word depending on the context. So each and every word, depending on the context, will be having its own embedding, even though so it means that same word can have different embeddings. Uh, So produces an embedding for each word from the input sentence, a group of words. For our system, we'll be using bidirectional encoder representations from transformers, which is also called as BERT. Moving further, after discussing the text encoder, we'll be discussing about the video encoder. So video encoder will be having two categories. The first is video level models, and the other one is a frame level models. So discussing the video level models, and they process the video to create an embedding. They process the whole video to create an embedding. Since it uses the whole video to process, it is computationally expensive. So you can see the working of a video level model where the input is pre-processed and given to the video model, and in getting the video embedding for the input video. The other one is a frame level model, where the frame level models runs runs in 3 steps. So pre-processes a video and sample frames, run the model on sample frames to create frame embeddings, and aggregate frame embeddings to generate the video embedding. So in the diagram below, you can see that we have an input video. After pre-processing the input video, the, the frames are created, and out of the frames, some sampled frames are created. Now those sample frames are given to the image model for creating their respective embeddings, and all of those embeddings are aggregated into one to create the whole to create the video embedding of the input video. So frame level models are faster and computationally less expensive. They do not understand the temporal aspect of the video, actions and motions. So frame level models are employed when temporal understanding of the video is not crucial. So let's say we have a video of one ball being being bowled to a batsman, and if it is important what the batsman hits is important, then we should not be using the frame level models, as it is a time based with this it's a time based event, and because of that, the frame level models do not understand the temporal aspect of it. If the batsman hits a six, or a batsman um, just hits any of the boundaries or something, then such models should not be created, because we are waiting for the result to happen in the video. Here we will be employing VIT, which is a visual transform. There are two reasons for that, which is improving the training and serving speed, and to reduce the number of computations. After after developing the model, we have to train the model. So for training the model, we'll be using the contrastive training method, where there is one positive from a total of n inputs. There is one positive that the input has to match, and from all the n minus one negative. So you can see in the diagram below that there is an input of the video. The video encoder is creating its video embedding, and there are other text queries which will have one positive or one matching query to the input video. So the text encoder will be creating the embeddings for all the text queries, and for further computing the similarities using the dot product, the we'll be uh, we'll be getting the output, and the softmax will be used. So a softmax function basically keep your output between 0 to 1. So because it is 0 to 1, it helps us to it can be treated as a probability, and so the outputs are always going to be between 0 to 1 using softmax. And using the cross entropy, we actually cross check the predicted probabilities between the ground truth or the real values and the predictions that are made by the machine or the model. So after training the model, we'll be discussing about evaluating the model. So there are two evaluations, the offline and online. So first, going with the offline evaluation, which is precision at k. The formula of precision at k is number of relevant items among the top k items in rank list divided by k. So k is basically the number of elements that are present in the output list that you decided. Let's say you decided to show 10 elements, so k will be equal to 10 in the output list. Or k can also be called as a cutoff from the range of outputs that you have decided to show. So in evaluation data set, um, a given text query is associated with only one video. So numerator equals to 1 and the precision will be low. Even if if we rank the video at top, so so precision at k and mean other metric which we call as mean average precision are not useful for in our case. The other one is a recall at k, which is number of relevant items in k divided by the total number of relevant items. So similar to the scenario discussed for precision at k, the relevant items, if the relevant items is equals to 1, the recall at k will be equal to 1. If it appears in top k videos, as it will be 0. So, so the advantage of recall is that it does measure the model's ability to find the associated video for a given text query. But the disadvantage is that uh, deciding uh, deciding the value of k could be challenging. So let's say there are two models A and B. If A ranks a relevant video at 15th position and B ranks the relevant video at 50th position, but if we decided the value of k to be equal to 10, then both of them will have the recall value equal to have the value of recall equal to 0, even if the model A was predicting the relevant video at the 15th position, which is better than the model B, which was predicting the giving the relevant output at the 50th position. So the third metric is MRR, where U is the number of list. You can see the formula for the MRR. So to calculate the MRR or the mean reciprocal rank, first we have to calculate the reciprocal rank of every list. So let's say we have 5 lists that we are considering for evaluating MRR or calculating MRR. Then all of those 5 lists, depending on the first correct result that is appearing in the five of those lists, and the reciprocal rank of all of them will be calculated and will be later divided by later multiplied by 1 into u and will be giving us the MRR. As the MRR will be ranging between 0 to 1, having the MRR of 1 or closer to 1 is a good metric to have. So the other category for evaluating the model is online metric. The first is a click-through rate. Click-through rate shows how often users click on retrieved videos or results. So click-through rate, clicked video, as a click-through rate basically shows whether the clicked videos are relevant or not. And in spite of this, sorry, the click-through rate doesn't necessarily show that the videos are relevant or not. So in spite of this, it is a good metric because it shows that users are clicking on the search results. The other one is a video completion rate. which shows a metric shows how many results appear in search results and are watched by the user till the end. So in video completion rate, the video watched partially, but is a still the video which is watched partially can still be relevant, but the metric alone cannot reflect the relevance of the search results. So there are some videos that can be used for the can be of use for the user until by only partially watching it, and the user does not need to watch the whole video. So that is what we are trying to say, that the video completion rate does not measure that fully. The third online metric is a total watch time of search results. So measures the total watch time of a user spend on watching the videos returned in search result. So basically, total watch time, having more watch time means search results are relevant and indicates how good the search results are. And in online metric, we can use all the three metrics for evaluating our model online. So this is basically the whole diagram of our whole system. The first one will be having the video indexing pipeline. The second one is a prediction pipeline. The third one is a text indexing pipeline. There will be a clear version of the videos, image as well. So, in the whole, so from the whole system, we'll be talking first about the prediction pipeline. So starting from the left of the image, we have a text query, which is dogs playing in outdoor. The text query is searched in two manner. First is the visual search. The second is the text search. So in the visual search, the text embedding computation will give us the embeddings, and will yeah, sorry. So the text embedding computation will be giving us the text embedding for the text query that is searched. And with the help of a nearest neighbor service, the videos that all the videos that we have will be searched depending on the text embedding that is given by the text encoder, and further passed on to the fusing layer. The other part of the text query is a text search, where using Elasticsearch and the indexing and getting the video indexing, the IDs from the video indexing table, and searching the relevant text search using the text queries. We'll be fusing the results of the text search with in the fusing layer. So the prediction layer has a visual search, which uses the approximate nearest neighbor algorithm. So basically, the approximate nearest algorithm you can see in the image down below. That the query that is searched is mapped in close proximity to the videos that are that we have, and all those videos you can see that the circled videos and will be given as a search result. The other one is text search, which using Elasticsearch for finding videos that matches the titles and text that overlap the search query. The fusing layer will be using search results of visual search and text search to produce a combined list of videos. And the re-ranking services incorporates business level logics as well as policies to modify the ranked list. So so we'll be discussing the video indexing pipeline, where the new videos where new videos are stored in the videos database, and then each of those videos in the video indexer, the first their indexes will be created, and the video encoder will be generating their respective video embeddings and will be stored in the video index table. Now, with the help of the visual search that we discussed here, the the queries that matches will be getting uh, getting the results from the video indexing table, which is in the video indexing pipeline. So a few points on video indexing pipeline. Video embeddings are generated by the video encoder, and these embeddings will be indexed, which will be used for used as a nearest neighbor services. The other one is a text indexing pipeline. The text indexing pipeline uses Elasticsearch for indexing titles and manual tags and auto-generated tags. So the textual aspect of the videos will be stored. So which are titles, manual tags, and descriptions. So let's say if the user has not given us or not uploaded, not given any kind of tags to the video that the user has uploaded. So in that case, we can use a auto tagger which can tag the videos, and those all of the tags, the manual tags that the user has entered, the tagger will be storing the auto tags in generated tags, and the titles, all of them are stored, and and the text indexer will be indexing all of those and will be saving it in the video indexing table. And using the Elasticsearch, we'll be retrieving the videos from the video indexing table. Sorry, text indexing table. Even though it's a video indexing table, it's used as a text indexing table. So even though we have discussed so this is and the search results that we are getting in the image. You can see that we are getting the search image. This whole system is a very simplified way that is actually used, or in real, it is very complex and can have a lot of improvements that should be needed, uh, or can have many improvements. So some other additional talking points on the system that we have discussed. The system can be multi-stage design. Means it can be divided into more different stages. Using video length or video popularity or extras, so more features should be used for video index for online evaluation and giving more better results. Instead of relying on annotated data sets, we can use interactions like likes and clicks and etc. and generate the data set which can be used for continuously training the model. And the fourth point is using an ML model which can find titles and tags which are semantically similar to the text query. So one whole different ML model should be used which can find titles and tags rather than using the embeddings alone. So let's just summarize the whole talk that we have done. So the first was clarifying the requirements, which was to uh, have a search query in terms of text, and based on the text query, we will be giving the results to the user. After that, we discussed about the framing as ML task, where we transform the requirements that we have into ML tasks and we first defined the ML objective. For text query, we get the search result, the results in terms of a list of ranked list of videos. We specified the input and output. Input was a text query, output was a ranked list. And then we discussed about the ML category and used representation learning. So in visual search. So in ML category, we discussed about the visual search, text search, and fusing layer. The visual search, we discussed about the representation learning, the video encoder and text encoder. In the text search, we discussed about the inverted indexing, which basically means that words were searched into the documents, and if the documents contain those words, those documents were given back. In the data preparation, we discussed about data engineering, but we were using an already annotated data set. So there was not much to discuss in data engineering. But in feature engineering, we discussed about preparing the data, which was a text normalization, where we discussed about normalizing the sentence or the text query that we will be having. So lowercasing the sentence of punctuation removal, trim white spaces, normalized form, compatibility decomposition, strip accents. So some of the characters have accents in them, so those are removed. The lemmatization, we talked about lemmatization as well as stemming, where lemmatization followed the dictionary form. The stemming did not follow a dictionary form. The Then coming to the feature engineering data preparation, we we talked about the preparing the video data. First, we talked about the text data, then we prepared about the video data, which was decoding, sampling, and resizing, and scaling. Then, then using uh, different methods such as set score normalization and correcting color mode. In the model development, we discussed about text encoder methods, where we discussed about the statistical methods of bag of words and term frequency inverse document frequency, which is TF-IDF, and machine learning based text encoders, which are embedding layer or lookup layer, word to vec, and transform based. In the video encoder, we discussed about video level models, where the whole video was processed to get the video embeddings. In the frame level models, took we pro- we took out some of the frames from the videos, and out of those, more sample frames were taken, and the embedding of the whole video was created or generated. After model development, we discussed about evaluating the model. So for offline metrics, we discussed about precision at K, recall at K, and why both of those methods were not of use for us in this use case. And we decided to go with MRR, which is a mean reciprocal rank. In the online metrics, we discussed about click-through rate or CTR, video completion rate, and total watch time of results. In While the model is working or deployed, so in serving, we discussed about the prediction pipeline, which was visual search. And so the text query was processed in two forms, which was a visual search as well as text search. And the fusing layer, which will be combining the result of the visual search as well as the text search, and re-rank before displaying the result to the user. The re-ranking services will be applied. Uh, Re-ranking services, basically the business logic as well as the policies, will be applied before giving it before displaying the list to the user. Then we discussed about the video indexing pipeline and text indexing pipeline. And later on, we also discussed about what kind of other improvements one can make or apply for it being the really simple model design for something that can be really complex in practice. So these are some of the references that were used in this presentation. So, so yeah, this is it for the ML system design for YouTube's video search. Thank you.
Jimmy, one first question from my side is,
Yeah.
what were the constraints when you started ML system design for this uh, visual search, visual ranking and all that? So, is there anything which you had knowledge about YouTube, like how many images, what, any such thing?
Like
Any
like a person. Are we like talking about the personalizing results or something like that?
Yeah, is it personalized or is it not personalized? What is the
Or
volume
it
of?
is no, for the simplification, it is not personalized because and it was only ranked based on the text query that we are getting.
So whether I use or you use, it will give the same result, right?
Yes, yes.
Got it. What about the what is the number of images you it searches? Is there any volume numbers, anything like?
For
Is it,
training,
yeah, for any so for training as well as for validation, right? So,
yeah.
so how many? So you showed two, two, four, and one five. Is that all, or how much? What is the volume actual?
So for
Is it?
training,
Uh, is it like billion or is it like million or what numbers
uh,
of
it,
images?
it is around a million to train the model,
Okay,
and
okay.
those and out of that the training set will be divided on
So
training, validation, and test type.
okay, so basically, if you say million images are there, 40,000 for training, 40,000 for sorry, 40,000 for building the model, 40,000 for validating, and then another
Yeah,
20 to do the test.
yeah, for
Something like
testing, eventually testing.
getting a hang of the volume. And
Yeah,
is it that you can't you give video as the input? You said text input, right? The input was a text and output is a video, ranked video.
yeah, rank list of the video.
Could you not have, could somebody not given video as the input then instead of doing just the text? But what
Uh,
would happen?
so right now I've only like no, studied about the text query based videos, but
Mhm.
of course if because the so what you so what we can do is show more similar videos depending on the videos that we have already searched. So let's say the text query giving us the video. So you click on the first video, and after the first video, the in recommendations we can show based on the similarity of the video.
So basically, the constraints have to be specified correctly at the time of design to be able
Yeah,
to specify the because these systems are very complex, correct?
yeah, yeah.
That's what. So I didn't hear about the constraints when you started. So I was just wondering. Uh, okay, you're converted that we have YouTube, everybody knows, so you pick something. But
Yeah.
what kind of volumes we are dealing in for a design, that is what I wanted to get some idea.
Yeah.
Thanks. Thanks for
So I will take
let
the
us ask questions. I will stop here. Thanks. Yeah, go ahead.
Uh,
Anybody? Go ahead.
on
Okay.
the
Yeah, go ahead.
on the same lines, may I? Yeah. Sir, whatever you asked must be possible because Google
yeah.
Lens works on those lines. We capture some image and we search for the request for the content or
Yeah.
its details, right? So there must be something already in place through Google Lens. Uh, Another query that I have is, Jamit, you mentioned about text and video search. Now, this text we are going to provide as a text input, right?
Yeah.
But and it is searching from the details. Is it searching from the image itself? Like, for example, some image has the content as a text, and
Yeah.
from the image itself, it searches that particular video or images, similar
Oh.
video or image. Is it possible?
So, so the text query that we are entering is
Huh.
it will be having two aspects, which one is visual search. So in visual search, we decided to go with frame level models, which will be exactly doing what you said. So the similarly similar. So the text query that will be uh, searched will be matched with the videos embedding, which will be created using the frames in the video.
So you mean the video embedding will contain the text that we have given submitted as a query?
Yeah, the similar, and there will be a similarity for the video embeddings that are created and the text embedding that will be created.
Okay,
Yes.
okay. A second thing that I have is queries you mentioned about YouTube, right? But
Yeah.
then, for example, I want to search for images of some disease. Yes, maybe MRI scan or something. Now,
Okay.
and there are already certain data stores like NCBI or
Yeah.
Japan database for DNA sequences and all that. Now,
Yeah.
and they have their interfaces also,
Yeah.
GUI interfaces through which we can search. But they are so complex and so detailed that we don't know exactly where to go and search and what particular should be the search
Okay.
query, right? So
Yeah.
if we have some search query on just anything, finding some data or finding some images for a particular kind of data that we want to work, we will
Yeah.
just apply the text query. It
Yeah.
should be able to crawl through different web pages or websites. So that crawling, is it
Okay.
possible? Do you have something on those lines?
Uh, I'm I'm like you are saying that you want the results for images in terms of text or in terms of videos as well.
No, images or videos, either. So basically, I want, for example, if we are working on some kind of disease through AI/ML, we need
Yeah.
some data sets, right? So
Yeah.
whatever known data sets are available, publicly available, these are limited images. So we can't work using ML or
Yeah.
DL, right?
Yeah.
So, but we want to search for more such images. So their
Okay.
crawling will be required.
Yeah.
Yeah.
Yeah, I
For
think
example,
web crawling
Yeah.
itself is a specific special case.
uh,
Here, what we saw was uh, in the text search, it did go to some websites, right? To pull up the web pages, you mentioned something in the text search, correct? So, besides the special databases which we want, we also want to pull out through web crawling.
yeah. So I think
Oh,
that will be another layer before AI, right? That
I think it would be a different kind of model or a component that should be used separately, which combines the result. If
yeah, and
we are
those
using
results,
about, if we are talking
yeah,
about this particular model, but if even if let's say just singularly doing exactly what you asked for, then something separately will be created, should be created, like search engine for data sets or something. or specific data sets or something.
Okay, and then those URLs should be submitted to your AI code, right?
Yeah,
Yeah. So okay, so that is one layer of one component
yeah,
prior to applying this AI.
yeah.
Okay, okay, okay.
So the AI here is basically just using this to find a good match for the search query. Here the training it is learning using the representation learning, but
Mm-hmm.
still it's not according to the search systems for the images or the other documents.
Okay. Yeah.
Yeah,
So,
probably
hmm.
web crawling, which you mentioned now, we'll have to take it as one of the requirements in the
Hmm.
ML system objectives. So
Yeah.
in the design, when we start, we say, hey, we here YouTube videos which are millions, and that it is already annotated, and we are just going to begin. That's different from the input. So the input has to be scrawled and got, and then the links have to be in that. Then the text search has to be conducted, and then from that, the relevance metrics can be brought in, and then for again we start after that using that we should. So that means there is a pre-processing as well as there
Hmm.
is a of the models.
Right,
Different
right.
models. So we'll have to add those independent of what this does. This only does what it says. It
Hmm.
only
Hmm.
does the
So,
video set. So we'll
so
have to
it would
add those.
be an application on the whole, a big
Yes,
application having different things, right?
correct,
Yeah.
correct. You're right. Makes sense that way. Yeah.
Or one of the things you can use which is based on RAG, retrieval augmented generations. The Perplexity AI uses the same thing. So basically, it you in a basic sense you can say that it acts like a web crawler or a web scraper that
Hmm.
it will refer to the document that is uh, based on which the it is answering you back for the query,
Hmm.
and so it's not using any kind of memory to remember the results or something, but it will just refer it back.
So, like for example, this I mean, just this is my curious question.
Sure.
This Chat GPT is connecting, it's generative AI, right? So first it fetches several pages across the web. Indirectly it is crawling, right? And it
Yes.
Correct.
identifies many web pages where that particular required content is, and then it formats a document where a single answer is generated. Okay. So
Yeah.
do you have any idea about how
Yes.
ChatGPT is crawling? And I mean, can we have some API of a
Yes.
ChatGPT where it is crawling and generating some URLs, and those URLs we save somewhere or in some document or in some collection and use those URLs for linking in our application, in AI application. So our
So
AI application will be working like a thread. Each request will be
Yeah.
an independent thread. Right now?
yeah. So what is there is one sorry Open.ai. There
Hmm.
are APIs available, and
Okay.
usually these tokens have certain size limitations and all. So
Yeah.
whatever prompt you give, it uses that prompt to fetch a bunch of things, and
Hmm.
that whatever it brings, if you want to, because the model is itself is model, right? We can't
Yeah.
edit the model. So what happens is there is a way to overcome that by having a pre-process. Once you send get something, then you can process on that, and there is a input addition. So you can refine with input addition, and OpenAI has. So what we'll do is we'll get to that sometimes in the future videos when we go into the Chat GPT and OpenAI.
Okay.
So
Okay. Okay.
there is definitely what you are trying to do is you are combining the uh, text, the large
Yeah.
language model NLP, along with what we are doing here, which is
Yes.
so
Yes, yes. And actually, that is the need of the day because we don't get things readily, right? We don't get things
Yeah.
readily. And we would like to get certain details, use those details for our processing, respect to our application, and then again use another application where it is already ready-made available. So we want to create a link between already two available applications for our purpose,
Correct. Correct.
right?
So what I'll
Uh-huh.
say is this we will be able to answer once we go through ChatGPT, uh, large language module, and NLP. He has only talked about BERT here, right?
Yeah,
So
yeah, yeah.
go about that, and then after that we try to mingle the two or mix the two and refine the way we want. So that is why requirement is the first step. What is our
Huh.
Yeah.
requirement? So,
Yeah,
and
yeah.
if we know this is our requirement, can it be translated into a ML task? If it can be, then what are the minimum inputs and what are the processing requirement? What the model? What are the data sets where we can get from? How will it acquire the data and create the model? Or if there is an existing closest model, that is what you take, right? You take that model and say, I want to enhance it for my use case.
Right, right, right. Huh.
So then the question is augmentation. How does one augment a given model and transfer the model and add our own inputs to the model, and whereby not even uh, what do you call having to do the grunt work of building the totally ground up model, right?
Right,
Ground
right.
up
Huh.
models are hard to build, very hard to build, and it's very uh, in it is very computation intensive also. So we want to reduce the computation also.
Hmm.
So, so I think all of those people who do PhD in this, they are going to face the massive amount of learning, how to optimize, how to get the best with minimum, and so it's a resource optimization game. And obviously, you can't get unlimited resources. That is the catch
True,
20.
true, true. And plus, whatever these resources are, whatever technologies, the cloud computing or whatever we say, but they always have the control in their hands, right? It doesn't give the control to the researcher. And plus, we have to pay above and over that we have to pay them. So that
Right.
becomes really impossible for a regular researcher, a normal researcher, typically in India. Even if we have some funding, it won't be available for those kind of things.
So what I have seen, like example, I have observed what Kisan AI,
Hmm.
Pratik Desai, Dr. Pratik, what he did was first he projected this is what he is doing, and
Hmm.
then he got the what do you call some 5,000 hours of some Microsoft support
Hmm.
and our Azure support. So he had to build
Hmm.
on Azure first before he
Hmm.
could build on his own.
Hmm.
So
Hmm.
one of them, somebody uses Amazon, Penny Lane, or whatever they have AI models. So
Hmm.
each one of them, what they do is they align with a particular thing and then break the alignment after some time,
Hmm. Hmm.
because freebie is available only till they believe that now they can scale. So they would like them to bump up into that at that before.
Ha.
So what the people do is they will use one against the other, Amazon, Azure, and then maybe something else, Google, whatever that. So they will try to do on multiple front together, but they will take free times from each one of them, and then finally come up with their own API and then put it. So it is a challenge. That is why startups are very difficult in this space, and you really need somebody with that kind of a. We'll try to get him. Okay, we'll try to get him to present in
And
our.
for yeah,
Yeah,
for these kind of work, you need a good team. A team of
correct,
at least 10 people working on different things simultaneously with a single aim in mind.
correct.
And that really becomes difficult in our scenario. Even at least in academic scenario, people
Mhm.
don't work across the universities, at least not in India.
Yeah, no, no, that is what we are trying to get to. The people have started understanding that if you want to do AI or quantum, you
Hmm.
need to collaborate across.
Hmm.
And if you don't have to, if you have 1 or 2%, there maybe they may be having 2 or 3%, and then pooling together we can get the resources. So those are the concepts we are trying to uh, uh, push through the EOTF, and you have seen that. We are trying everything, including we are trying to entice vendors to sponsor so that they can
Hmm.
use their resources and eventually learn to build and then figure out whether they want to use that or not, right?
Hmm. Hmm.
It's not that you have to use that vendors. No, no vendor we want any we don't want any vendor dependency. Unless the business makes a financial sense, then that they can decide. But as an academician, we want to do research, right? So
Hmm.
for research, we want to just see, okay, I want to try out whether I can separate an apple from an orange using some library of somebody. And then tomorrow I may replace the library with something else, right?
Hmm. Hmm.
So, so this is a collaborative approach, and that is the difficult part to explain. And once people have tried it, then they realize that they need collaboration. That is where the role of EOTF comes in. We try to push together. Like I know that Ramanujam College does a lot of stuff, and you do something. Same way SIT Pune does something, or the CDAX. So if you can pull together the people for the sake of benefits of all of them, because you can always share what you did, right? Provided you have some kind of a at some arrangement.
Right.
So start collaboration is itself a first thing, and then having a arrangement and agreement so that it doesn't get into nasty IPR issues, which is what we want to avoid.
Hmm. And then there is another game also. Like, see, somebody like me, if you ask me to sit and work on the computer for 15 hours, if this was 10 years back, I would have happily done, right? 10 hours, 20 hours, that would be fine with me. But now, if you ask me to do, I won't be able to do even for 2 hours. But the
Correct,
ideas that I can generate and the direction that I can give is my experience, right?
correct,
That
correct.
that probably nobody would have. So
Absolutely
it has to be have a collaboration of people who can think and a collaboration of people who can work. Both
correct.
is required.
Yeah,
So
you are on dot. You are on dot. See, this is where the challenge is. So, what is true with you is true with me also, for that matter. That
hmm,
is, people who have experience, they cannot do hands-on coding at this time. And plus, code is generated through Chat GPT or some generative. Why do you have to sit and code? Correct.
hmm, hmm.
So we need somebody who can do that after understanding what is the so requirement is the first step. And if we
Yeah.
miss the requirement, something wrong, then it
Huh.
will go very difficult to account. That is why all the time when we present a use case, we want the requirement. What is the requirement? Give us
Hmm,
a little bit
hmm.
more detail before we, because there are many ways to do, and
The same
some,
thing. Yeah.
but something can complicate it, something can be simplified. So what is best? And that is the reason for this study circle. Whole idea
Hmm.
is we study and figure out and we collaborate and uh, help each other at the end of the day. That's what the idea is.
True. True. Yeah.
So,
That's
Nikhil, Amina, anybody, anything? Yeah, we can. We know we have been discussing, but we want you also to participate. Let us ask anybody who has anything to ask.
yes. Amina,
Go ahead.
any queries? Please come forward. Amina, are you there?
Yes, she's there. It's
Yeah.
just that. Do I need to? Okay, let me do one thing. Let me. Uh, Amina, I can get the muted. I can unmute her. Unmuted. Yeah, go ahead, Amina. I have unmuted you. Are you able to get it? I think she's probably not. Anybody else who wants to ask any question? Nikhil, Dhirendra?
No,
Yeah.
no questions from.
Yeah, go ahead, Nikhil. Oh, okay. Yeah, go ahead.
No, actually, I am here to just learn because I mean that's what it says, you know.
Yeah,
So
go ahead.
I yeah. So I'm just starting in AI. I
Mhm.
mean, uh, and just learning things, trying to get as much as my head around what's being discussed over here. And I'm more of a practical person rather than uh,
Theory, yeah.
yeah. So
So,
that
Nikhil,
yeah.
where are you from? You are from Bodhifalia side there, Murray side?
No,
Name suggests you. Hmm?
Yes. So my house in Mumbai,
Okay.
Borivali East.
Mumbai East, Dombivli East. Okay. So
Borivali East.
Borivali. Okay. Borivali. That is, yeah. Okay. That is
Yeah,
Gujarat side. We call it
yeah, yeah. But my native place is in Ratnagiri.
Ratnagiri. Okay.
I'm, yeah.
Good. Good. See, join, and even if you are from different university, it doesn't matter. We want people to learn, and that's
Yeah.
important. And ask questions. Prepare. Go watch through all the four videos which Jamit has.
Yeah. So
Fifth
where
one.
can I get the previous question? I mean,
Yeah. Yeah. So there is a. Let's put in the chat window. There is a. Uh, One sec. We had done it in the past. Let me see if I have it. No. Okay. I'll get you. Give just a second. I can get you in the meantime. EOTF. I have it on the website. Uh, Give me a second. It's under collaterals, and I think I can hopefully get it. Yeah. So this is YouTube videos, right? Yeah. So I think I got it. Let me put it on the chat window. So here is the uh, here is the text www.youtube.com at OT. What is it? I think it is.
yeah,
Yeah,
it's open text forum.
yeah, it has got. Now it was mine was light, so was not able to. Yeah. So you can use that OTF uh, OpenTech Forum 1140 OpenTech Forum 1140 slash.
Yes.
So in the playlist there will be playlist for AIML, and if you go into AIML then there will be many. So you can follow at least four are there already, and fifth one we can. I'll,
Uh, yeah, it says 7 videos. So I think this would be the eighth one, right?
this will be eighth one. So you also have previous videos. If you have not seen one, two, three, four,
Mm-hmm.
EOTF. This is ML system design 1, 2, 0, 1, 2, 3. This will be four.
Okay, okay.
So you can watch the videos and come back next time. And we are planning next time for ML system design for harmful content detection. You can see here. So
Okay.
how to harmful content we'll try to project that. So that will
So,
another.
like, this would be like harmful content over live internet. Is it like, would it?
Yes. Yeah.
Okay.
Yes. So if you want a ML system to capture all the harmful content in the what do you call the videos and all the streamings and all that, so we'll try to get that, and then so that's
Yeah.
why I said no. We, the use case once we say no, then we describe what it is and how it is, and next time Jamie will do that. And in the meantime, we are also having one more 14th, no 17th, I think Saturday next Saturday we have one more. After that Saturday we'll skip. We'll have that one of the conferences which we are planning, workshop type thing.
Okay.
More than that will be 8 hours from different universities. Like some people from Delhi, some from Pune, some from Baroda, some from Chennai, and so
Mm.
all these people present. And there will be different topics like quantum and AIML and maybe some
Okay.
cloud related also. So join the meetup group that we have, and we'll try to get you more. Okay.
Yeah, yeah, yeah. Sure.
And thanks
Thank
for
you.
participating.
Yeah, yeah. Thank you. Thank you.
Yeah. Anybody? Dhirendra, go ahead. You have your. Yeah.
Uh, yeah,
Yeah.
yeah. I'm audible, right?
Yeah. You're audible. Yeah. Go ahead.
Yes, Mr. Prakash. Actually, to be frank, I am working as a IT administrator, server administrator, and I have over 10 plus year experience on
Mm-hmm.
that field. Now
Mm-hmm.
I'm looking to switch over my career as a AI ML developer. So I just
Mm-hmm. So, yes, it is a good
yeah,
beginning.
yeah. Sorry. So I just want to
Good.
know how it would be difficult for me, as I am from no programming background.
Correct. So, that is what, if you remember, Dr. Mamta mentioned that uh, your experience, whatever is there, IT experience, that how can you correlate to ML platform usage, right? Because trying to go to the coding side, coding codes can be generated. That's not the issue, but ML, whatever design is there, how do we optimize? And to optimize, you need to use a lot of GPUs, and a lot of people don't even know what GPU is, whereas you will be
Yeah,
knowing, right?
I'm no. Yeah, I'm know
So
all the things. Basically, actually, I'm working for a company which is also working on AI ML. But
correct,
just don't have any background. I mean, programming background.
correct, correct. So the actual, if you look at no AI ML is supposed to have no coding, right? Low coding, they say.
Okay,
That means
okay,
you should be able to pick up the already existing code and apply. It is more of a model development, right? So it is to more to do with the data
okay,
science, data science,
okay,
data engineering, then modeling,
okay,
and then you talk about in the modeling you may require algorithm coding. That is different. Our algorithm may also be pre-built, so you may not need any coding. So it is not coding intensive. So don't even
okay,
need to
okay,
think of coding as the way, but think of it.
okay.
What is the pipeline of processing? Where can
Right,
I
right.
fit in?
What
Where I
should be?
can? Mhm. Yeah.
Yeah,
Go ahead.
what should be a path to start from? I mean, beginner.
Yeah. So what I would say is this is a very a large topic, but to give you a summary, you look at the pipeline of machine
Okay,
learning, because
okay,
if you talk AI is too vast. Machine learning is very specific. How we
okay,
enable a machine to learn, and that means there is a algorithm. So if you do algorithm, then there is a pipeline. How do we automate that pipeline? So I would say that trying coming from a hardware and a systems background, it would be more appropriate to go towards ML system operation, pipeline processing and all, rather than
okay,
specific application.
okay, okay.
Because
Good.
any application comes, how do I use it? It has to do the same thing, right? There is a
Right.
seven-step process we are doing. You go through these videos. There is a seven-step process. You have to identify what is the problem. How do you learn? How do you make machine learn this? What is the data
Right.
component? What is the validation requirement? What is the model building requirement? What is the testing requirement? And how do we evaluate if it is doing what we want? So there is a benchmarking. So basically, the whole process end to end is very hardly understood by uh, junior people. They only know that I have to
Right.
give this and I have to get the output. So there is more to it than just coding. So I would say if you start coding, that is for the hobby, it's fine. But if you want to really leverage this as a career, then go into the operation part of it. Getting my point? Dhirendra? Yeah. I think Dhirendra, you got Dhirendra, where are you from? Where are you located?
I think he
Please
disconnected.
disconnected. Yeah, yeah.
Okay, okay, no problem. No problem.
Yeah, he
So
came
Okay,
back.
okay, okay,
yeah,
okay.
okay, we'll
Thank you.
yeah, yeah. Oh, he's saying thank you. Okay. Anybody else has any questions? And do come back again. We'll have more discussion as we go. Okay. I
Yeah,
think
okay.
we are out of time. Is that right, Jamit? We are 140. I have to stop the
Yeah,
recording.
yeah,
If we
no
stop
worries.